In this lecture, we're going to learn how to find the forces in truss members using the method of sections. I mentioned in the earlier lecture that there are two methods to solve a simple truss problem. The first method is the method of joints, and the second one is the method of sections. In the method of sections, a truss is divided into two parts by taking an imaginary cut through the truss. So by doing that, we're going to expose each internal force as external to the free body diagram. So for example, if you have a truss member, which is a two-force member, and the force this member is subjected to tension, is pulling it apart. Now we're looking for the force developed within this truss member. So we're going to run an imaginary cut at any location along this member. By doing that, we now have two segments, the top and the bottom. So if the entire truss member is in equilibrium, then each part of the truss member is also in equilibrium. So to complete the free body diagram of each segment, for example, for the top segment, we expose the internal force as externals now. And because of equilibrium, this internal force, now it becomes external, must be the same magnitude of the applied force here and also opposite direction, which means it's also a pulling force or also tension. Same idea for the bottom segment. For this bottom segment to be in equilibrium, the internal force must also be same magnitude of the applied tension and opposite direction, which means it's also a tension because it pulls this bottom segment, tries to pull it apart. And those two forces are action and reactions. They are the same magnitude and opposite direction, according to Newton's third law. Same idea if we have a member which is subjected to compression using the same imaginary cut method, which is the method of sections. We will have two segments, the top and bottom. For each segment to be in equilibrium, we can see those internal forces must also be compression and is identical or is the same magnitude as the applied compression on the force members. So in conclusion, equilibrium requires that the member in tension be subject to a pull, whereas the member in compression is subjected to a push. And now we're looking for the applied tension applied to the end of the member. But if we can use the method of sections, if we can find those internal forces, they are kind of the same magnitude and same pulling or pushing force. So instead of looking for those applied forces, we can look for the internal reactions. Same idea as the method of joints. Instead of analyzing each member connected by the pin, we're analyzing the pin, which becomes a equilibrium of a particle. And now for the method of sections, we have the equilibrium of rigid body problem. And now we have two methods to choose from, method of joints and method of sections, and which one to choose. Basically, when we need to find the force in no more than 3 members of a truss structure, then we can analyze the truss using the method of sections. So when you recall all the problems you did with method for joints, usually you are asked to find the forces in all the members. Maybe there are 5 members, maybe there are 6 members. So we need to go around the structure to analyze one pin after another. But sometimes if we just need to find the forces in 3 truss members or 2 truss members, then the method of sections probably is the method we're going to choose. The fundamental principle of method of sections is that if the truss is in equilibrium, then any segment of the truss is also in equilibrium. Let's see how to use the method of sections. We're given this simple truss structure, but instead of looking for the forces in all of the members, we're only looking for forces in member BC, member CG, and member GF. So the method of sections runs an imaginary cut or section through the members of interest. So in this example, we're going to do a cut just through those three members. So now this truss structure will be separated into two segments, the left and right. And we're going to draw the free body diagram of one of the two parts. We can choose either the left segment or the right segment. Then we're going to apply the 2D rigid body equilibrium equations, because now we're not having a particle, but it's a rigid body. So we're going to apply the EOEs to the part to determine the member forces at the cut section. And keep in mind, for a single 2D rigid body free body diagram, we can only solve up to 3 unknowns. That's why we said when we are looking for the forces in no more than 3 truss members, the method of sections is what we're going to choose first. Okay, let's apply those methods and steps to see how to solve the forces developed in BC, CG, and GF. So the procedures of analysis, first we need to decide how you need to cut the truss or section the truss. And this is based on where you need to determine the forces. So since we're looking for the forces in member BC, CG, and GF, so we need to run a cut across those members. And second, we need to make sure we do not cut more than 3 members, because we can only solve up to 3 unknowns. So after that, decide which side of the cut truss will be easier to work with. So before we see which one is easier to work with, let's just draw the free body diagram of both segments, the left and right. And then we're going to decide which section we're going to use. So to draw the free body diagram of the left segment, this is what it looks like. So we draw the outline structure of the left segment and place the applied force. And for those truss members, those cuts, the internal forces now are exposed as externals. So the force FBC, because all the truss members are 2 force members, so those internal forces are along the direction of the truss member, so along BC direction. And same idea, the FCG is along the CG member, so we call it FCG or FGC. And the last force is the internal force of the GF member, FGF. So in this example, I'm assuming the 2 forces FBC and FCG are tension, because they are pulling away from the member, where the FGF is a compression because it pushes into the member. And also you want to indicate the relative location of the forces, because the FBC and FCG, they are concurrent. They will joint. The line of actions joint at point C. So this will help us to write the equilibrium equations later. So we want to indicate the relative relations of those forces. So typically those forces, every 3 or 2 forces are concurrent about a point. Okay, two forces are concurrent about a point. And this will be our free body diagram of the left segment. We have one given force, we have three unknown forces. Now, the internal forces are exposed as externals, and the free body diagram is about this left segment is a rigid body. And we can write three equilibrium equations. For the right segment, if we're going to draw a corresponding free body diagram, they'll look like this. So first of all, since it's a free body diagram, we need to remove those supports at pin D and pin E. So D is a fixed pin support, so there will be two support reactions. We need to place two support reactions at D, and there's one support reaction at E, which is perpendicular to the supporting surface over here. And in addition to that, we have the three forces we're looking for, and those are the internal forces. Again, after this section, it will become externals. And here you can see the relation between the FCB on the left segment and FCC on the right segment. They are action and reactions. Action and reaction. So they are of the same magnitude but opposite directions. But another way to identify or to describe those forces are, if this member BC is in tension, then all the segments or the entire truss member is subjected to tension or will be pulling away from the forces. So this FBC on the left segment is in tension, so on the right segment is also in tension, and they have the same magnitude. But based on, if you draw the x-axis, we can see those two forces are opposite directions, one pointing to the right, one pointing to the left. And same idea for this FCG on both segments. Those two forces are also action and reaction. They have the same magnitude, and both of those forces are tension. In other words, FCG is pulling up, and then FCG on the right is pulling down. So they are opposite directions. And same for the last pair of forces. They are action and reactions as well. Same magnitude, but opposite directions, but in a sense, both of the forces are compression. So those are the two free body diagrams of the left and right segment respectively. So we just need to choose one segment only, because we see those internal forces are essentially the same. We don't have to calculate them twice, right? So my question is, which one will you choose given the two free body diagrams? You can pause the video and think about for 5 seconds and check your answer. Well, if I'm going to solve this problem, I probably will choose the left segment. The reason for that is we don't need to solve support reactions if we choose the left segment. We only have one applied force and we have 3 unknowns. We can solve them directly. But if you choose the right segment, the first step is to figure out those support reactions. And how to figure out the support reactions? Well, we need to draw the free body diagram of the entire truss and solve the support reactions first. So for the entire truss, it's just a 2D rigid body problem. We have we can just put the support reactions here. This is dy and dx and ex. So for this entire truss, we don't have to think about the internal details, just look at the outline of this structure. We have one applied force, we have 3 unknown forces, and use the free body diagram of the entire truss, we can solve the 3 unknowns, and we solve those internal reactions. So again, clearly the left segment is much easier to use.